Okay, let's begin this week's activity with an RC circuit. The characteristics of behavior of a series RC circuit are discussed in a little more detail in the slides. So you can see how the relationship between a capacitor, which you can see right here I have set at 0.05 farads, and a series resistor, which you can see I have set at 15 ohms, connected to an AC power supply. You can see the frequency of the AC power supply is 0.2 hertz. You can see the voltage on the AC power supply is set at 100 volts. Now, this RC circuit, as we call it, it's unlike the DC RC circuit that we talked about previously, because the capacitor does not come to a full charge because of the alternating current. It goes in and out of charge and discharge modes, which actually makes it act more like a resistor in an AC circuit than it does in a DC circuit. In a DC circuit, it eventually stops the flow of current entirely after it's fully charged. Here, because of its time oscillating between charging and discharging, it just acts as something to slow the rate of current flow, and it acts like a resistor. Now, how to compute the series resistance between a capacitor and resistor? You don't just sum their individual resistances because of the phase relationship of their currents. Their currents are 90 degrees out of phase. So you can't add their resistances directly. You have to use Pythagorean's theorem, really, to add them. And again, look on my slides. It shows the recipe for finding the resistance, which in an AC circuit we call impedance. So it shows the recipe for finding the impedance of this AC circuit. Now, I'm not running it right now. Again, remember, because of the weirdness of the relationship of current and voltage, and because of the oscillation of current and voltage, it's a little more instructive to plot the voltage and plot the current. I don't have the circuit running right now. When I hit play here, we should see the current and voltage time dependence appear on the graphs, and I'll hit that now, and here we see them. So I'm showing now the time dependence of them. It's a fairly broad wave because the frequency is only 0.2 hertz. Okay, so that means every 5 seconds there is one period of the wave, or there's 0.2 complete cycles per second. So it takes 5 seconds to complete one wave. If you were to compute the period of this wave as 1 over 0.2, so this is a very broad wave. You can see if I do again a stop here, and let me move it a little. I'm going to move it so the voltage it comes to a max, and I can be real careful here and get the voltage. As advertised, the voltage is varying between plus 100 volts and minus 100 volts. While that is occurring, let me zone in on the max of the current. I'm going to stop it now. I'm at about the max of the current. You can see it's just a shade under 5 ohms for the max, and a little bit less than negative, I said 5 ohms. It's a shade under 5 amps for the maximum current, and it's almost negative 5 amps for the minimum current. Now, what you should be able to do using the recipe on the slides is, with these characteristics shown, you should be able to compute what the Z or impedance of this circuit is, and you should be able to calculate the current. That will be something you will be asked to do in your lab report. Okay, let's move on to a so-called RL circuit. An RL circuit contains a resistor and an inductor connected in series. You can see I have a resistor here on the right. It's a 100 ohm resistor. I have an inductor, or we could call it a coil, or we could call it a solenoid. It's just a loop of wires. Sometimes it has a core in it to increase its behavior of holding magnetic field in it. And this particular inductor is set at 25 henries. So I have them connected to a 100 volt AC power supply, this time at a frequency of 2 hertz. So there's 2 complete cycles of the wave every second. So it has a period, if you like, of a half a second. Every half second, one wave finishes. So every second, 2 complete waves finish. Now, it's not running again. We don't see any variation of current or voltage yet because I have the play stopped. Now that we've talked about the characteristics, let's let it roll and see what the behavior of this RL circuit is. Now, the first thing I'm sure you will note is that this frequency is way greater than the frequency that I had for the RC circuit. This frequency is actually 10 times greater in frequency, and the reason behind that is that capacitors only act like good resistors at relatively low frequency. Inductors act like good resistors at high frequency. So they will have a lot of ohms to their impedance when the frequency of the circuit is high. So I necessarily had to set a fairly high frequency of 2 hertz. Believe me, normal frequencies of AC circuitry is 60 hertz. So that's some 30 times higher in frequency than this. So you get an idea that this is relatively slow even for conventional circuits. Okay, now again, when you connect a resistor and an inductor in series, you can't just sum their resistances as you would for nearly normal series resistance components. There's a phase difference in the relationship of their currents. They are again 90 degrees out of phase. So essentially what you have to do is a Pythagorean theorem, sum of a squared plus b squared to get c squared, to get the total resistance of this circuit. So again, you can turn to the slides for some more information on that. I can take the inductive reactance value, square it, add it to the square of the resistance, take the square root of that, and that'll give me the series resistance of these 2 components. Now again, let's stop the circuit so we can get a look at the characteristics. Again, I've moved the voltage to the origin, and I see it's going between, as it should be, plus 100 and minus 100 volts. And at the same time, the current, now I've changed the scale on this to make the readings, the current is going between more than 0.25 down to below negative 0.25 amps. So when we have a 100 volt current, when we have these characteristics in the circuit, a 100 ohm resistor and a 25 Henry inductor operating in a 2 hertz circuit, we're getting a current reading on the meter of a little bit more than 0.25 for the max current and a little bit less than negative 0.2, a little bit more actually if you want to say it that way, than negative 0.25 for the current on the low side. So what you're going to do in the lab report here is use the recipe to get the impedance of the RL circuit. You can see that in the slides. Then you can calculate the current from the impedance voltage relationship, again, as you can see in the slides. So you'll do that for your lab report. Let's move on to an RLC circuit. This has a series connection of a capacitor of 0.05 farads to a resistor of 15 ohms to a coil of 15 henries inductance. They are connected to a 100 volt power supply that has a 0.3 hertz, or a third of a wave, if you like, 3/10 of a wave per second frequency of the voltage and current. Okay, now again, these components are connected in series, but you don't sum their apparent resistances because of their phase difference of their relationships. The capacitor and inductor are 90 degrees apart from the resistor, so you have to do some kind of Pythagorean relationship to connect them together. But interestingly, the capacitor and inductor are 180 degrees out of phase. Again, look at the slides to get a little more background on that. So literally they work opposite of one another. While one is charging, the other is constantly discharging. It's really interesting, and we'll touch again on that on our next slide, our next examples as well. So since they are 180 degrees out of phase relative to the current, again, when one is charging, the other is discharging. So one is depositing current while the other is impeding current, and vice versa. So they really kind of cancel each other in the circuit, and you have to do the recipe to calculate the total impedance of an RLC circuit based on what you would see in the slides. Now, right now, of course, again, it's not running. So when I start to run this, you'll see that I'm getting now some current and voltage relationships. It's some intermediate frequency of the wave here, because this is 0.3 hertz this time. And again, if we look at what's happening for the voltage, it's going from Vmax of 100 down to Vmin of minus 100. And what's happening with the current is it's an Imax of less than 5 down to an Imin of not quite negative 5. So what you should be able to do is to calculate the ZLRC, RLC, or whatever I call RLC, I believe I call it, using the recipe on the slides, and see how it compares to the I max and I min that we're seeing if you calculate using that impedance divided into the voltage. See what you get for the I values that this circuit should produce. Now, there is also a very interesting and very weird relationship between the voltages that are dropped or added or consumed by each component here. Remember, in a DC circuit, as you go your way around, each component drops the voltage so that the total voltage drop is equal to the output voltage of the meter. Here, though, the inductor and capacitor are actually in some ways contributing voltage to the circuit. So there is some kind of Pythagorean relationship between the voltage of the components of the circuit. And again, you should see the slides to get those values in their entirety. Now, what I'm going to do is I'm going to connect the voltmeter across the resistor, and you'll notice we're getting a wildly varying voltage that's hard to make any sense of. Here's what I'm going to do. I'm going to run it step by step and see what the maximum, okay, I'm up to 55, 57, 58, 60, 61, 62. I'm approaching Vmax dropped on the resistor, 63.28, 63.94. It's slowing, so I'm going to bet that's the maximum. 63, it was 63.9 was the, oh no, what I'm saying, 64.4, still going up, 64.65, 64.7, that's probably going to be about it. And I see the next one was down. So 64.7 is close to the peak voltage dropped by the resistor. You should be able to calculate the peak voltage dropped, and I'm probably not right at the top of the curve, so I'll be asking you on your report to calculate the peak voltage dropped on this and see how it compares to what we were able to measure. Now, I'm also going to measure the voltage change across the inductor. This should be a pretty crazy value. maybe even more voltage than the supply of the system, because the magnetic field of the inductor stores quite a bit of energy and allows it to dump a lot of voltage itself. Oh, let me step it up. Now notice already it's 103. I'm going to keep going up. Let's see how close I can get to Vmax across the solenoid. 113, 115, 117, 118, 120, 120.89. That might be it. Oh no, not quite. 121.31. This has got to be it. 121.35 is as close as I can get to Vmax across the inductor. Now remember, the current or the voltage itself is only supplying 100 volts. This is able to put out more than that itself because of its storing energy in that field, and that's a very important trick that is used in the behavior of these things when you put them in circuits. Now if we go across the capacitor up here, not surprisingly, it's some different potential. Let's see how much output I can get from it. 45.6. I'm going down, so let me see if I can get it on the way up. I'm still on the way down here. Let's just find the negative Vmax, since that's where I'm at. Negative 14, negative 19, negative 21, negative 26, 8, 30, 32, 33. I must be approaching it. Negative 35.5, 37.1, 38. Okay, I must be slowing down now, I guess. No, I'm not. I'm still going. Negative 43.9, negative 44.5, 45.08. Okay, this has got to be close now. 45.76, and that was it. As close as I can get to Vmax on the capacitor is 45.76. You should calculate it yourself using IXC and see how that compares to what we're measuring here. And you can do that again for your report. Okay, now let's play a little bit with an LC circuit. An LC circuit has an inductor or coil and a capacitor. And let's first go over the characteristics of what we got here. I have 2 ammeters you can see hooked at the bottom. I have a capacitor on the right and an inductor in the middle. You should note that they are connected in parallel. Okay, notice that the inductor and capacitor are not connected right in the same circuit current to each other. They're after junction points to each other. So the current will split and flow into the inductor, and separately another current will flow into the capacitor. On the left, I have a switch which is now open, as you can see, and also I have a power supply here that interestingly is not of the AC type. I have a DC 100 volt DC power supply, no frequency, it's direct current. So the current will flow out of this is the positive side of it, it'll flow out of here in a positive sense and return to here in a negative sense if I were to close the switch. Now then this 100 volt power supply will deliver voltage equally to the inductor and capacitor to begin with. Now I have a voltmeter across the capacitor reading nothing right now because I have the circuit open. I also have a couple charts over here that have nothing registering on them. Actually, the circuit is actually running right now. I can stop it, or it doesn't really matter. I stop or run it. So let's just let it run. And let's close the switch and watch what happens here. First, you will notice very quickly there isn't a resistor in here. So there's going to be very high current flowing into the capacitor. And once the capacitor completely charges, it will stop the flow of current. You should see this voltage go up to 100 very quickly, but then this will drain and run through the inductor, and pump all kinds of juice through this inductor, and will probably overheat this circuit because of all that. But I close it. Notice that went up to 100 very quickly. Now it is falling with some kind of LC thing. And notice I'm burning up the circuit here. And now what I'm going to do is just open this. And I want you to notice what starts happening. Again, let me close it just to show you again. When I close it, there's current flowing here. It quickly is rising and rising and rising, and it's going to start burning up my capacitor as it goes over a certain value. There's no more current flowing on the right. Now when I open this, notice there's no more current flowing on the left. This is an open loop, but I have current flowing through the right being fed by the capacitor and the inductor. Now the capacitor and the inductor are oscillating the energy they store in them between one another. Notice how this current is varying. It's going up to a very large amount, then falling to a very low amount as the current oscillates between the inductor and the capacitor. Now, if I were to put these meters on here, notice I will get a voltage flow across the inductor, and I want you to notice what my scale is set on for the voltage output of the inductor. It's going from below negative 600 or so, that's probably down up to about positive 700 volts, down to negative 700 volts. Now remember, I only charge this with 100 volts. You can see how an LC circuit can give you an incredible voltage advantage by the energy you store in the electric and magnetic fields. So there's essentially a 700 volt potential being output by this inductor. And notice that it's completely sinusoidally oscillating. It's perfectly periodic in nature. Now it's a fairly slow oscillation, which means that it's a fairly low frequency circuit. For your lab report, I'm going to ask you to calculate that frequency from the L value of, well, I don't even have the inductor up there, do I? Let me put the inductor thing up there. Let's show what the inductance is. Right now the inductor is set on 10 Henry, or sorry, set on 50 Henries. Oh, excuse me. So I have a 50 Henry inductor. I have a 0.05, farad capacitor. So you should be able to calculate from 1 divided by 2 divided by pi divided by 1 over the square root of L times C. You should be able to get the frequency with which this circuit should be oscillating. And we could compare that with what we're seeing here. I'm seeing 2,875. This is like about a 2.5 second interval between times that I'm seeing on that scale. You should be able to calculate the LC frequency of oscillation. Now remember, there's no AC power source in this. The alternating current is being solely supplied by energy stored in the inductor, switched to the capacitor. The capacitor drains and charges the inductor drains and charges the capacitor. This oscillates back and forth. This, folks, is the secret to how a radio circuit acts. We can oscillate this circuit at a certain electromagnetic wave frequency and actually pick up that electromagnetic wave, and you can make a radio transmitter or radio receiver from this very same trick. This is exactly what Marconi did some 150 years ago when he invented the radio. Now, again, I'm going to ask you to calculate the natural frequency of this circuit based on the components that you're seeing in this circuit. We see that this is a completely oscillating circuit, even though it does not have an AC power supply. And this is just a little taste of what you can do with capacitors and inductors when you put them in circuits. And believe me, the wizardry of signal transmission and reception is all based on this phenomenon.